Okay, so now we're going to turn our attention to AP topic 9.2, and that is second derivatives of parametric equations. And the idea is really not that hard, it's just the work is a little taxing at times. But basically, the second derivative of a parametric equation just requires you to take the derivative of the dy dx, so take the derivative with respect to t of the first derivative that we worked on in the last lesson, and then set that over the dx of dt. So basically, the steps are this. Find the first derivative, like we've already learned. Then you find the derivative of that first derivative with respect to t, and that will go on top of a fraction bar. And then write that answer over your original dx dt that goes on the bottom. So let's take a look at an example of this. So the instructions might say something like, find the second derivative of y with respect to x when y is sine of t and x is e to the 2t. So let's see what happens here. So we'll do what we've already learned. We're going to take the first derivative. Dy over dx will be the derivative of y with respect to t divided by the derivative of x with respect to t. Now the derivative of sine of t is cosine of t, and the derivative of e to the 2t, a little chain rule there, bring out the 2, and then e to the 2t. So there is the first derivative. So now let's find the second derivative of this. So what we need to do is we need to find the derivative with respect to t of that first derivative that we just found. So we're going to, we have to take the derivative of that, and then we're going to divide it by the dx dt that we already have on top, already have there, the 2 over, or 2 times e to the 2t. Okay, so here we go. Now, this might require a little bit of side work. We need to take the derivative of that first derivative. So we're going to say, okay, well, what is the derivative of this? And you see we're going to have to do the quotient rule. So the derivative of cosine on top is negative sine of t, and that's times the bottom. Then we subtract the top times the derivative of the bottom, which in this case is again, chain rules to bring out the 2 again. So we get 2 times 2 in front of e to the 2t. And all that is over the bottom getting squared. So you can see things get kind of messy really fast. So I'm going to take all of that and write it here in where we're working on our answer. Now sometimes the stuff on top can be added together in various ways. This one really cannot, so we will say negative sine t 2e to the 2t minus cosine of t 4e to the 2t. There might be some random trig IDs that you can use there. I don't know. Okay, so we now need to bring the denominator over, and so that will be the 2e to the 2t squared. We're going to distribute that squared. We'll get 4e to the 4t. And then we need to put all of that over this dx dt that we have. So we're going to put all of that over 2e to the 2t. Now, you really need to look at ways to simplify this for multiple choice questions. And so we already said the numerator of the second derivative part we cannot simplify. But we do have that over 4e to the 4t divided by 2e to the 2t. And so whenever we multiply by that reciprocal, we end up with this. Negative sine t 2e to the 2t minus cosine t 4e to the 2t. And then all over 2 times 4 is 8. E to the 4t times e to the 2t, you add your exponents, e to the 6t. And so there we go. That is the second derivative of these parametric equations, y equals sine t and x equals e to the 2t. The idea isn't difficult, and it's just doing a lot of derivatives that you've done for a while. but it's just, it gets messy. Putting together like terms gets messy and that kind of thing. Okay, so there is one other thing that we can do, and that's this second step. So now that we know how to get a second derivative, just like with functions, you can use that second derivative to determine the concavity of a polar curve. So we can use a first derivative to determine find the slope, and I guess you could also find relative mins and maxes and those kinds of things. But we can use a second derivative then to find concavity. So let's do another problem where we will work on that. So maybe the instructions will say something like find the concavity of we'll get a point, so we want to find it at this point. We'll say the point 1 comma e, and we're going to do it of these parametric equations: x equals 2 to the third and y equals e to the t. And so to find the concavity, we need to find the second derivative at that point, and then we can determine if it's a positive second derivative, then it's a concave up. If it's negative, it's concave down. So here we go. So we need to find the first derivative. So dy dx is the derivative of y with respect to t over the derivative of x with respect to t. So the derivative of y, e to the t, that's not too bad. That's just going to be e to the t. And then the derivative of x will be 3t squared. So there you go. Not too bad. We're doing good so far. So now let's. There's nothing to simplify there. We're great. So now we want to find the second derivative of y, and with respect to x, and so that's going to be the derivative with respect to t of our dy dx that we just found over the derivative of x with respect to t. So we need to find the derivative with respect to t of this dy dx that we just got. So I'm going to do that over here in a different color. So we need the derivative of that. Well, okay, look, we have a quotient property again. So the derivative of e to the t stays e to the t. The derivative of times 3t squared. Then we're going to subtract that. The first thing times the derivative of the second, which is 6t. So we'll put that 6 in front, and we get that t there. And I'm going to rewrite that 6t e to the t. I like that better. All right. Okay, so something really unusual happens on this problem. Let's discover that in just a second. And so all of that then is over the denominator squared, so 6t to the fourth. Okay, actually something does unusual. I was kind of looking ahead and thinking about something else. Okay, so there's our derivative with respect to t of the first derivative. So we're going to write et, and I'll tell you what, I want to bring that to the front as well. So let's go 3t squared et minus 6t et all over 6t to the fourth. And then that's over the original derivative of x with respect to t, which is 3t squared. So we'll write 3t squared there. All right, so here we go. How can we simplify this? Well, there are a few things we can do. First of all, it looks like we can simplify some of this stuff that's on the top. It looks like we can factor out a 3t et, and that leaves us with a t and a minus 2. And then on the bottom we have 6t to the fourth times 3t squared. So we'll go 6 times 3 is 18. T to the fourth t squared is t to the sixth. Okay, so we have a second derivative. Oh, look, we can actually reduce the 3 and 6 to, or 3 and 18 to 1 over 6. We can take a t off there and make that t to the fifth. So let's clean that up even more. E to the t times t minus 2 over 6 t to the fifth. Okay, I like that better. All right, so that is our second derivative. Wow, what a mess. We want to find the concavity at 1, 2. Now, here's the deal. Our second derivative is with respect to t. So there's, or not 1, 2, it's 1, e. I can't read my own writing. So we can't plug 1 or e in because that's an xy point. Okay, let me clean this up. I apologize. That is 1, e. Okay? All right, so what we need to do is we need to find the time that makes 1, e. And this point, 1, e, it has to work in this set of parametric equations. So you can plug the 1 into the x and solve for t, or you can plug the e into the y and solve for t. They both will give you the same t, or else that's not a point on the polar curve or plane curve, and so then it's the problem is moot and there's no point to it. But let me just show you what I mean. So if we plug the 1 of the point in for x, so we get let's get out of green, let's go blue. So we'll go 1 equals t to the third, and then whenever we solve for t by taking the cube root, we find out that the time is 1 that makes that point x1 ye. Now we could have also found that by plugging the y part into the y parametric equation. So we'll go e for y equals e to the t, and of course t equals 1 makes that true. So you don't have to do it in both. You don't have to test it to make sure you're right. It'll work in either one, x in the x or y in the y. So we have a time now. Let's highlight that. We have a time now of 1 that we can plug into our second derivative t's to find out if it's concave up or concave down. So hey, we are almost there. These two problems, but a lot of work. So we have the second derivative of y, and we want to evaluate that at t equals 1. So we'll go e to the first times 1 minus 2 over 6 times 1 to the fifth. So that's 1 minus 2 is negative, so negative e over 6 times 1 to the fifth over 6. That is a negative second derivative, which means that we are concave down in these parametric equations. Sorry about that. So we are concave down for these parametric equations, x equals t to the third and y equals e to the t, at the point 1, e. There you go. It's a mess, but it's all stuff you can do. You just have to be careful and work things out nice and slow. All right, thanks.